Bismillahirrahmanirrahim. Dear students, today we are going to discuss about Polonovski reaction, which is basically the formation of carbon-nitrogen bond. The ingredients used for this conversion include nitrogen oxide species, or you can say tertiary amine oxides, N-oxide of tertiary amine. This substrate is treated with acyl halides or anhydride to get the amide and an aldehyde. The nature of the products can be varied, can be changed by changing some conditions or some mechanism, route of the reaction, by applying some specific reagents. That is, we can obtain from this reaction by using a set of conditions as amide and aldehyde, and we can also obtain from this reaction enamines, or we can also obtain alkenes. We can also convert this into an amine. So these different nature of products depend upon the conditions provided to these this reaction. So this is basically all about of the Polonovski reaction, which provides different a large number of nature of products, but today we will specifically discuss about the formation of amides and aldehydes, which is the basic Polonovski reaction, and we shall confine ourselves to this discussion only. The key concepts of today's lecture are: first, the simple introduction, brief introduction to Polonovski reaction, and then overall mechanism, revision of overall mechanism, and then there will be discussion of some modifications given to this Polonovski reaction, and some general features of this reaction, along with some synthetic applications which have been used in the synthesis of different organic moieties or functionalities. In 1927, Polonovski brothers, these were two brothers with a similar suffix of Polonovski, so therefore this reaction is also termed as Polonovski. So these brothers were working on the natural product chemistry, and they prepared an acetyl derivative of alkaloid by using alkaloid N-oxide, and they moved towards the cleavage of alkyl groups, which was attached to this nitrogen, with which oxygen is also attached, and we are naming it as N-oxide. They used acetic anhydride or acetyl chloride for this purpose, and after then a lot of work on this step, on this way of reaction, it was recommended best method for the demethylation of tertiary amines. Demethylation means the removal of methyl group from the nitrogen of a tertiary amine in very mild conditions through this reaction. This is mild condition is because the other methods available for the demethylation of tertiary amines require vigorous conditions as compared to this one. So this reaction was preferred for this step, for this process of demethylation of tertiary amines. First of all, the tertiary amines N-oxides are taken and they are activated by the use of acyl halides or anhydride, and this activation results into the formation of iminium ion intermediate. This iminium ion intermediate has stability which varies depending upon its formation, and in some cases it acts at the same time. As soon as it is formed, it is converted into the further steps. But in some cases, which is also termed as the modification of Polonovski reaction, we can convert this amine into many other useful products depending upon the nature of the nucleophiles used for this purpose. Here you can see the overall reaction of this Polonovski. First, tertiary amine N-oxide. N-oxide, because oxygen is attached to nitrogen, is converted treated with acetic anhydride here using DCM as dichloromethane as a solvent along with pyridine, and you get an amide and an aldehyde. Here you can see the aldehyde, the alkyl group, which is converted into, which is present in the aldehydic functionality, is that one which is attached on the alpha carbon. That is the alpha carbon is you can see the basic requirement for this for the progress of this reaction. We shall discuss the mechanism, then you will see how this alpha carbon plays an important role in the formation of these products. So R2 group is coming from that group from which alpha carbon has been used for the progress of the reaction, and other two groups which were already attached to the nitrogen directly remains on the nitrogen, and we get amide and an aldehyde. Here is the review of the overall mechanism with respect to anhydride. We have discussed that first, nucleophilic attack of oxygen of N-oxide on electrophilic center carbon of anhydride. After acylation, we get the N-acylated product, and then the abstraction of alpha proton by the acetate ion, and followed by the elimination of acetic acid, we get the amine formation. This alpha carbon of amine is then again attacked by a nucleophilic acetate ion, and we get the alpha acetyloxy derivative. This compound again interacts with another molecule of anhydride, and after at first step and at the second step, the acetate produce acetate ion attacks on the carbonyl of acetyloxy group, and we get the product of amide and aldehydes. This is through intermolecular interaction. This can also proceed through intramolecular interaction in which nitrogen attacks on the acetyloxy group present at the alpha position, and after through the formation of a four-membered ring, it is converted into the product of amide and aldehyde. Here is the second mechanism with acyl halide, which we discussed, followed the similar pattern of mechanism as with the anhydride, but in case of anhydride there was the counter ion of acetate ion, but here in this case the counter ion will be a halide and a halo group. Almost all the steps are similar to that one which we have discussed for the anhydride, and first the interaction of oxygen with the acyl carbonyl of acyl halide, then the formation of acetyloxy group at nitrogen. After the removal of abstraction or alpha proton by the halo group, we get amine. This amine is interacted with the acetate ion to form alpha acetyloxyamine. This alpha acetyloxyamine can move through intermolecular or intramolecular interaction, and we move towards the product. First is the N-acylation, formation of amide, and then the attack of halo group on the carbonyl or acetyloxy group removes the acetyl halide back, and with the formation of aldehyde and amide. The first modification was given by Potier of this Polonovski reaction, that instead of acetic anhydride, trifluoroacetic anhydride was used as the reaction initiators and catalyst for the formation of iminium ion. And the main feature of this trifluoroacetic anhydride was the iminium ion produced is much stabilized, and there we can use this produced iminium ion for the formation of a variety of compound by using different types of nucleophiles. But in case of acetic acid, simply the iminium ion is more easily or rapidly converted into the product side of acetamide and aldehyde. So there are less chances for the separation of iminium ion in case of acetic anhydride, but in case of trifluoroacetic anhydride it is much easy. Here you can see the example. First is the reaction in which N tertiary amine oxide is converted into iminium ion by trifluoroacetic acid, and then this iminium ion is converted into alpha cyanoamines, that is cyano group is attached at the alpha carbon of this nitrogen, and also in a good yield. Here you can see the mechanism. First here the molecule is amine is taken a cyclic one. First the similar type of mechanism has been followed, which we have discussed in the last lecture and also in the previous slides. That oxide acting as a nucleophile attacks on the carbonyl of trifluoroacetic acid, and we get the acetyloxy substituents after the regaining of carbonyl, and then this acetate ion abstracts the proton from alpha carbon, and we get the double bond at carbon nitrogen, that is aminium formation, along with the removal of the acetate ion. So this is the formation of iminium ion. This iminium ion is then reacted with a nucleophilic cyano group or cyanide ion, and this cyanide ion attacks on this carbon, and we get the carbon nitrogen single bond, so the formation of alpha cyanoamines. The nucleophile, if we change this nucleophile, for example we use a Grignard reagent, then let's suppose we use phenyl magnesium halide, then phenyl acting as a nucleophile will be attached at this position. So a variety of molecules have been obtained by this from this iminium ion. Here we shall discuss about some other types of reactions which also moves through the formation of this iminium ion. This is the second modification, in which another reagent, that is alpha silyl oxyamines, that is we move through the silylation through the use of silyl group contained. Here you can see in this case is tertiary butyl dimethyl silyl triflate has been used as an activating agent instead of any anhydride or acyl halide, and we get the intermediate of alpha silyloxyamines, which are converted into iminium ion after the elimination step, and then in the end after the attack with the nucleophile. Here you can see the here in this case nucleophile is the phenyl magnesium halide, and so first is the attachment of methyl lithium, reaction with methyl lithium, that is and then second is the phenyl magnesium halide, and here you can see the attachment of phenyl group at the alpha carbon of nitrogen. The alpha carbon in this reactant N-oxide, there was present alpha carbon, and now this alpha carbon is nucleophilic attacked by phenyl from this Grignard region, and we got the product. This step moved on the same mechanism, on the same basis as we discussed for the Polonovski reaction, but due to different nature of the interacting species and nucleophiles, we have obtained different types of products. So iminium ion is a versatile intermediate, and which have been used for the synthesis of a lot of number of compounds. The third modification discussed here is the formation of enamine. Here you can see tertiary amine N-oxide is treated with acetic anhydride, and we get the yield of 82%. And here the formation of product is a tertiary amine with a double bond between alpha and beta carbon. So we are with the product of enamine. Basically formed first the nitrogen N-oxides are converted into nitrogen halide. Here we as we say it as enamine by using acetic anhydride as activating agents, and then this adjacent atom of nitrogen atom gives the alpha acetoxyamine, which we have discussed in the last slides also. This intermediates then can be hydrolyzed to give aldehydes, or can be moved through elimination to give the enamines or alkenes. Here are given some general features of Polonovski reaction. First we have seen that N-oxide is used as a substrate which can be synthesized from tertiary amines after oxidation. And then this N-oxide tertiary amine is treated with different activating agents like acyl halide or anhydride, but in majority we use acetic anhydride. Although it is less reactive compared to acyl halide, but the other factors like stability, like toxicity, like solvent nature of byproducts, anhydride has been preferred due to mild reaction conditions. Iron salts and sulfur dioxides can also be used as activating agents, but the nature of products is different for these iron salts. Also the formic acetic anhydride or formic pivalic anhydride, pivalic means trimethyl acetic anhydride, the nature of product is also changed, and we get amines in these cases. So you can see here overall reaction. First the tertiary amine is oxidized into N-oxide tertiary amine, then if it is treated with acetic anhydride or acyl halide, then we get the classical Polonovski reaction, which is the formation of an amide and aldehyde. And if we treat it with iron in its ground state or zero oxidation state, or its 2 state, that is ferrous, it can be ferrous, it can be simple iron, we get then amines instead of amide along with the formation of aldehyde, and this is termed as a non-classical or iron salt mediated Polonovski reaction. We shall discuss the mechanism of this iron as a catalyst for the formation of amines in the next slides also. Here is given the mechanism for the iron salt, which act as activating agents and form secondary or tertiary amines depending upon the nature of the substrate. Here you can see at the first step tertiary amine N-oxide is protonated, and we get the oxide O into OH group. The positive charge of nitrogen is counterbalanced by the anion of the acid. For example, here if we use HCl, then it will be chloride ion. This is only for the simplicity of understanding that I am mentioning here HCl. Normally for the acetic conditions we do not use HCl. Whichever the reaction, when we have to give some acetic conditions, normally we use sulfuric acid or some other organic acid, but we mostly avoid this the use of HCl. Now this positive charge of nitrogen is counterbalanced by the negatively charged chloride ion. Then this salt is attached with the ferrous in coordination through transition. As you know, ferrous is a transition element, so through secondary valency there is a complex formation. Then when another molecule of acid proton comes, this proton is obtained by the OH group and we are left with the formation of water. And when this nitrogen oxygen bond is broken, oxygen one electron is given to the oxygen OH minus, which interacts with H plus to form water, and nitrogen gets its one electron, unpaired electron. Positive charge is already present on it, and now this positive charge is counterbalanced by the chloride ion which was already present with it. The second chloride ion in this step which has come with this proton, this second proton is attached with the ferric which has been formed due to oxidation of ferrous into ferric. Now you can say the electron lost by ferrous is given to this chloride ion, and so these two are counterbalanced, and the positive charge of nitrogen is counterbalanced by the previously attached chloride ion. If this unpaired electron is again removed from this nitrogen, or you can say is an unpaired electron is given to this nitrogen to form a lone pair, then in the form of when ferrous is converted into ferric, that is oxidation takes place and the lost electron is given to this nitrogen, and we get nitrogen in the form of lone pair, and the chloride attached with this nitrogen is now attached with this second ferric ion, and we get the tertiary amine here. Second route of the reaction can be with the elimination of HCl, that is the chloride ion present with this with the ferric ion Fe3 is now abstracting proton from CH3 group alpha carbon, and it is removed in the form of HCl, and ferric is converted back into the ferrous with the removal of electron, and this removed electron is given here, and we get in the form of CH2 group. CH3 is converted into CH2, and the two electron between carbon, as H plus is removed, so carbon hydrogen two electrons are moved towards this carbon nitrogen bond, and we get double bond here. Nitrogen gets a positive charge which it has already here is because it has 4 bonds, and its one unpaired electron now paired up by that electron which is lost by the reduction of ferric into ferrous, and after hydrolysis we again get the tertiary amine along with the formation of aldehyde. So this is the overall mechanism for the formation of amines from N-oxide tertiary amines in the presence of iron salts. Here are some examples of some different reactions which also use the formation of iminium ion as intermediate. Here is the example of Mannich reaction which uses a secondary amine and aldehyde and ketone with alpha carbon in the acidic conditions, and we get the product bearing amine and ketonic functionalities. Here this one part synthesis. Here you can see at the first lone pair of amine interacts with the aldehydes to form convert it into OH group, and then this is converted into with the removal of water into iminium ion, and this iminium ion then interacts with the other enol which is converted prepared from the ketonic functionalities to form the product. So this reaction also uses the iminium ion as an intermediate for the formation of new compounds, but this iminium ion is prepared from tertiary amines and an aldehyde in acidic conditions. Here is another example of Pictet-Spengler reaction which is used for the synthesis of isoquinoline, and here you can see the primary amine is treated with aldehyde in the presence of acid to form the isoquinoline, and here you can see the formation of aminium ion, that is first the ammonia lone pair ammonia is interacted with the protonated aldehyde, and we get the intermediate which after protonation and removal of water forms the iminium ion, and this iminium ion acting as an electrophilic center interacts with the benzene ring and form the cyclic ring for the formation of isocoanoline. So this reaction also uses the iminium ion for the synthesis of heterocyclic compound. Another feature of Polonovski reaction is the formation of two types of categories of products depending upon the nature of the conditions. Here you can see that depending on the nature of activating agent and reaction conditions, there are two main reaction pathways available for the iminium ion to convert into product. First is the formation of iminium ion, and second you can see the reaction. One is nominated with A and second is B. A type is that which we have discussed, which is classical Polonovski reaction, that is tertiary amide and then aldehyde, and second is the case in which alpha beta bond, alpha carbon that is attached to nitrogen through double bond in iminium ion, and the next beta carbon, this bond is broken and it is activated by an electron donating group, electron donating center which is present adjacent to it. Then if this carbon alpha and carbon beta bond is broken, then we get the B category product, that is one is alkene and second is the new iminium ion, which can be moved further into the different products. Another condition for this bond cleavage is that the C alpha and C beta bond is anti-periplanar with the N-oxide and nitrogen oxygen bond. Anti-peri means matlab anti-parallel. That is if on one side is NO bond, then on the opposite side of it there will be C alpha C beta bond. The acidity of alpha CH bond is increased by the electron withdrawing group R1. If R1 group is an electron withdrawing group, then this alpha carbon will be more acidic in character and proton will be easily removed during the path of the reaction, and we can get the products more easily. Another point which should be considered for this reaction is that if nitrogen tertiary in tertiary amine oxide, if nitrogen is bearing more than one groups, it is understood there will be 3 carbons attached to nitrogen. But if they have more hydrogen at alpha position, more than one groups are there which have hydrogen at their alpha position, then what will happen? It is shown that regioisomeric iminium ions are formed, number 1. Number 2, the regioselectivity can be controlled. How it can be controlled here? That is, if we use trifluoroacetic anhydride, then we get the thermodynamically more stable iminium ion, and which is most of the time a endocyclic iminium ion. And if we use acetic anhydride, then it is kinetically more acidic alpha position is deprotonated, and also we get exocyclic iminium ion, and the formation product is according to that iminium ion. Here is the example of a cyclic tertiary amine oxide. In the presence of acetic anhydride, you can see the alpha proton of methyl group is deprotonated easily, and we get aminium ion in the exocyclic form, which moves through the other steps of this product, and we get at then amide and aldehyde and acetic anhydride as the byproduct. You can see it is the reactant which is acting as a catalyst. here is the example as we discussed. The cyclic tertiary amine N-oxide reaction only for 5-membered and 6-membered rings is known, and also with endocyclic amine in preference to exocyclic ones, and this is also in the presence of trifluoroacetic anhydride. But in case of simple acetic anhydride, there is the more capability of exocyclic amine instead of endocyclic amine. And here is the example in which you can see the cyclic 6-membered cyclic N-oxide, which is treated with trifluoroacetic acid, and we get the cyclic amine, which after abstraction of proton from beta carbon, we get enamine, which then on further reaction with trifluoroacetic anhydride, we get the formation of trifluoroacetyloxy enamine. Here I give some synthetic application of this reaction. Here you can see the first reaction in which metachloroperoxybenzoic acid has been used for the oxidation of this tertiary amine into N-oxide tertiary amine, and then it is treated with trifluoroacetic acid in DCM at -20 degrees C temperature with 1 hour stirring, and we get the iminium ion formation. And this iminium ion then converted with sodium sodium borohydride, and we get the again tertiary amine. Then what is the difference in the, as you can see, in the reactant side and the product side? If you see keenly, then the stereochemistry of the reaction has been changed a lot. Before the formation of iminium ion, the stereochemistry was too much different, and after the formation of iminium ion, the stereochemistry has been changed. And we get the drug or synthetic molecule. Similarly, in the second example, here you can see the hydrogen peroxide is used for the oxidation of tertiary amine into N-oxide, and then on treatment with trifluoroacetic acid in pyridine and DCM, we get the formation of trifluoroacetyloxy substituent with enamine formation, and this is after multiple step has been converted into amide. In the drug, here you can see ultimycetin. Here are two examples which are related with the use of acetic anhydride. Here first example is also with the first is the oxidation of amine, and then with the reaction with acetic anhydride for the formation of acetyloxy group or derivative, which after a number of steps has been converted into the product. Likewise, second example is also first oxidation of amine and tertiary amine, and then second reaction with acetic anhydride, we get the product in which there is OH group, which you can see with red color is inserted here in place of the hydrogen, and after a number of steps we have been converted into the product. So these are the some examples for this Polonovski reaction, and this is all about today's lecture, and thanks.